They say giants walk slowly. But some don't just walk, they evolve, contract and hide the immensity of their past beneath thick clouds and deep magnetic fields. Out in the cold, churning reaches of the solar system, a world orbits so colossal, so ancient, that it shaped the destinies of planets before they even had names. But now, scientists have discovered something astonishing. Jupiter, the mighty gas giant we thought we understood, was once far more massive, vastly more powerful, and perhaps far more influential than anyone had realized. According to a landmark study published May 20th, 2025, in the prestigious journal Nature Astronomy, Jupiter was once at least twice its current size, and its magnetic field was a blistering 50 times stronger than it is today. The research was led by planetary scientist Konstantin Batygin at Caltech and astrophysicist Fred Adams at the University of Michigan, two leading voices in the field of planetary evolution. This isn't just trivia. This discovery could reshape our understanding of how the solar system formed, how gas giants evolve, and what ancient planetary giants might still be lurking in systems beyond our own. To grasp the significance of Jupiter's ancient size, we have to step back into a time before Earth had a moon, before Mars had valleys, before even the Sun had fully stabilized. Roughly 4.5 billion years ago, the solar system was born from a swirling, collapsing cloud of gas and dust called the solar nebula. As gravity drew the cloud inward, a star ignited at the center, our Sun, and the leftover gas began coalescing into planets. Jupiter formed first, rapidly becoming a gravitational titan. Its formation ended the planetary possibilities for some neighboring regions. By sweeping up gas before others could form, it may have prevented a larger planet from ever appearing between Mars and Jupiter, leaving behind only the asteroid belt. But while Jupiter's present is massive, this new study shows its past was truly titanic. In the final phases of planetary formation, just as the gas in the solar nebula was fading, Jupiter ballooned to more than twice its present radius. It was still hot from formation, glowing with residual heat, and large enough that it may have radiated with a faint, reddish light, a giant, smoldering ember in the early night sky. For a time, Jupiter wasn't just a planet. It was a force of nature. Here's where it gets clever. To measure the size of ancient Jupiter, Batygin and Adams didn't look at the planet itself. They looked at its moons, specifically Amalthea and Thebe, two small inner satellites orbiting close to the planet. These moons are often overlooked, especially next to Europa or Ganymede. But they've been quietly circling Jupiter for billions of years, and their orbits preserve ancient clues. Over time, their paths have shifted due to the gravitational pull of their more active neighbor, Io, a moon constantly reshaped by volcanic forces. However, these orbital nudges from Io don't quite match what scientists would expect unless Jupiter's gravitational pull was once much greater. By studying how far Amalthea and Thebe's orbits had drifted and modeling how much influence Io should have had, the researchers worked backward. They concluded that Jupiter's larger past radius perfectly explains the discrepancy. Think of these moons as the planetary equivalent of tree rings or fossilized ripples, quiet witnesses that carry echoes of a forgotten age. But it wasn't just size that set ancient Jupiter apart. It was power, specifically magnetic power. Today, Jupiter has the strongest magnetic field of any planet in the solar system. Generated by metallic hydrogen swirling deep beneath its clouds, this magnetic field drives radiation belts and fuels some of the brightest auroras ever seen. Yet during its youth, the team found Jupiter's magnetic field was an estimated 21 milliteslas, 50 times stronger than it is now, and about 400 times more intense than Earth's. That level of magnetic energy is hard to imagine. Its reach could have stretched millions of kilometers into space, bending charged particles, distorting the young solar wind and influencing the formation of surrounding objects. Some researchers suggest that this massive magnetic shield may have altered the migration of planetesimals, the rocky building blocks of planets, and helped funnel volatile materials toward the inner solar system. The result? Ancient Jupiter may have played a role in seeding planets like Earth with the water and organics that made life possible. Its magnetosphere wouldn't have just been impressive, it would have been defining. The story doesn't end in the past. In fact, Jupiter is still shrinking today. According to researchers at Caltech, the gas giant continues to contract by around 2 centimeters per year. This slow collapse is caused by the Kelvin-Helmholtz mechanism, a process where a planet radiates internal heat into space and over time cools and compresses. It's like watching an ancient starless furnace burn down millimeter by millimeter, eon after eon. The outer shell settles inward. The core becomes denser. Its magnetic field weakens. Its radius contracts. Jupiter is a planet still forming, just very, very slowly. And that shrinking isn't just a curiosity. It has real implications for how we understand other gas giants, especially the mysterious hot Jupiters we find around distant stars. Many of those exoplanets appear bloated, much like our Jupiter once was. Are we seeing snapshots of other planets in the stage Jupiter passed through billions of years ago? In that sense, Jupiter is a Rosetta Stone. By studying it, we not only understand our past, we also glimpse the futures and pasts of alien worlds light years away. This revelation of Jupiter's immense past doesn't just tell us about one planet. It helps anchor the entire solar system in something astronomers love, a benchmark. Models of solar system formation are complex, filled with uncertainties. But what Batygin and Adams have uncovered is a hard observational constraint. A point in time, a real size, a real field strength, a real phase in evolution. It's a cosmic calibration point. From this, scientists can better understand the forces that shape not only gas giants, but the entire dance of planetary evolution. It may help answer long-standing mysteries, like why the solar system only has one gas giant inside Jupiter's orbit, or why Earth's early bombardment period was so intense. This benchmark changes the game. It means the early solar system wasn't a calm nursery. It was a battlefield ruled by a magnetic giant. Today, Jupiter spins serenely in its orbit, 484 million miles from the Sun. Its clouds swirl in ribbons, its great red spot churns slowly, and its dozens of moons continue their eternal dance. But beneath those clouds lies a buried past. A planet once hot, inflated, and wrapped in a magnetic storm that might have spanned the solar system. A giant that sculpted the paths of planets, shaped the survival of worlds, and left scars in the orbits of moons too small to fight back. Now, thanks to this new research, we can see that ghost. And we realize we've been orbiting its legacy all along. If stories like this spark your curiosity about the cosmos, subscribe. There are more ancient truths waiting to be unearthed about our world, our galaxy, and the giants still hiding in plain sight.